In this video, I'm going to show you how to do two different kinds of problems related to the Fibonacci sequence. These will be like problems you'll see on exams, and we will work on them in class during the next class period. So pay very special attention to notation and how important it is that you write each expression on your paper correctly so that you can read them later and come to the right conclusion. So this is problem 7 in section 2.2. As you notice at the beginning of this video, I suggested other problems you could try on your own. We'll be working some of those in class, and I wouldn't be surprised if you saw one of them on your exam. Discovering Fibonacci relationships. By experimenting with numerous examples in search of a pattern, determine a simple formula for f sub n squared plus the next Fibonacci squared, f sub n plus 1 squared. That is a formula for the sum of the squares of two consecutive Fibonacci numbers. So there's lots of words there. And the key to being able to learn mathematics is to understand what each one of those words means. You know that this is the nth Fibonacci number, and this is the next one. So look, a formula for the sum, it's right here, the sum of the squares, notice each one of them is squared, the sum of the squares of two consecutive Fibonacci numbers. Consecutive means that they occur one right after the other, like 21 and 34, or 89 and 144. They are consecutive, right next to each other in the sequence. So we'll start working on this problem now. This problem is number 7 in the textbook in section 2.2, Discovering Fibonacci relationships. By experimenting with numerous examples in search of a pattern, we want to determine a simple formula for this expression right here. F sub n squared plus f sub n plus 1 squared. That is a formula for the sum, here's sum, of the squares, these are both perfect squares, the sum of the squares of two consecutive Fibonacci numbers. Every word must be understood before you start a problem. That's the key to being able to understand what you're doing. Consecutive, of course, means that they are right next to each other in the sequence, like 21 and 34 are consecutive Fibonacci numbers. It means f sub n and f sub n plus 1 for any value of n. So, of course, we can't see what this would be right away, so I want to give you a way of attacking a problem like this where you can find a pattern. Okay, so I wrote the expression f sub n squared plus the next Fibonacci squared there, and we're going to take at least 5 values of n and just see what we come up with. So I'll just do it right down the side, and you can model this if you want. Let's let n be 1. If n is 1, then what we want is f1 squared plus f sub 2 squared, right? If n is 1, then n plus 1 is 2. And looking at our list here, we see that the first Fibonacci is 1. The second Fibonacci is also 1. So the sums of squared is 1 plus 1, equals 1 plus 1, or 2. All right, well, that's what we got. So we can't see a pattern unless we have several examples. So let's write n equals 2. In that case, this expression here that we're trying to find in general, that expression, I don't know why that happened. When n is 2, will be f2 squared plus f sub 3 squared. When n is 2, n plus 1 is 3. So the second Fibonacci is 1, 1 squared. The third Fibonacci is 2, so we'll want 2 squared, is equal to 1 plus 4, or 5. Remember, we want to do at least 5 examples. If n is 3, then f sub n is f3, the third Fibonacci squared, plus the next one, the fourth Fibonacci squared, would give us, well, f3, if you count over, that's 2 squared, and the fourth Fibonacci is 3 squared. So we get 4 plus 9 is equal to 13. All right, so now let's let n be 4. I already see a pattern, don't you? We got 2, 5, 13. Those are Fibonacci numbers, but let's see. Let's do 5 of them. So if n is 4, this expression up in the box is f4 squared plus f5 squared, which is f4 is 3 squared and f5 is 5, so that will be 5 squared. We get 9 plus 25 is equal to 34. It is another Fibonacci number. So we're seeing a pattern here. We are getting Fibonacci numbers. But let's do n equals 5. It's always good to have 5 examples. f5 squared. When n is 5, then n plus 1 is 6, so we have f6 squared. Notice how I'm very careful to write my subscripts down, my exponents up, so that I can read it well. f5, the fifth Fibonacci is 5, so this is 5 squared, and the sixth Fibonacci is 8, so that's 8 squared. 25 plus 64 is 89. So we have 5 examples, and we certainly do notice that these are Fibonacci numbers, all of them. But that's not enough of a pattern, because we want to complete that generalized formula. We want to be able to write f sub n squared plus f sub n plus 1 squared equals, and have something to say in general here. We know it's a Fibonacci number. The sum of those squares is a Fibonacci number. So what question naturally comes to mind? Which one? Which Fibonacci? So that's what we have to answer. And the best way to do it, let me change colors here. The best thing to do now, we ask, which one? Whoops, that didn't change colors. Which one? Which Fibonacci? Well, we'll go up and answer that question on these 5 examples. 2 is the third Fibonacci, so I'll write F3. 5 is the fifth Fibonacci. 13 is the seventh Fibonacci. 34, count over up here, 34, you will see is the ninth Fibonacci. F sub 9 and 89, no surprise, it's going to be F11. Well, we see something else now. We see that it is a Fibonacci and that it is one that occurs at an odd position in the sequence, the third position, the fifth one, the seventh, ninth, or 11th. We know that the next one is going to be F13. So we could, if this question asked you, what is the next one, F6 squared plus the 7th squared, you know it's going to be the 13th Fibonacci. But how can we say this in general? Well, go back here and look. When n was 1, we had F3. When n was 2, when n was equal to 2, we got F5. Let me write that right here. N was equal to 1, n was equal to 2. I got F7 when n was 3. Got F9 when n was 4. And F11 when n was equal to 5. So I think, the way I would look at this is I would try to find a formula there in terms of n. Notice if you double the value of n and add 1, you get the number 2 times 1. Let's see, over here, 2 times 1 plus 1. 2 times 2 is 4 plus 1 is 5. 2 times 3 is 6 plus 1 is 7. 2 times 4 is 8 plus 1 is 9. So it's twice n plus 1. Okay, so that's, I'm much more experienced, so I would see it that way, and I would write fn squared plus fn plus 1 squared is equal to f sub 2n plus 1. And notice it works. Now, students often, they see it a different way. Let me take red there and show you how they look at it. They see F3 and they notice that that's 1 plus 2. They see F5 and they notice that that's 2 plus 3. F7 here is F3 squared plus F4 squared. So they notice that it is the sum of those two subscripts. And so here's how they write the answer. They say Fn squared plus F sub n plus 1 squared is equal to a Fibonacci. And they write down here n plus 1. And that's absolutely fine. That's the same thing as 2n plus 1, isn't it? N plus n is 2n. So you can find the pattern in different ways. Notice the first thing we did was we looked at 5 examples. We found them by just plugging in n equals 1 through 5. Then we noticed that we had a Fibonacci number, so we were partly there. And we said, well, which Fibonacci? So we took our 5 examples and we wrote which one it was. Then we had to try to find a formula. That's the hardest part of the problem. But if your notation is excellent, it's much easier to see the pattern. This is another interesting fact about Fibonacci numbers. You've always known, or at least you've known since middle school, that every natural number can be written as a product of prime numbers, a unique product of prime numbers. And that's been very useful to you. That's why you learned it while in middle school. But also every natural number can be written as a sum of distinct, meaning different, non-consecutive, they're not right next to each other, Fibonacci numbers. Every natural number can be written as a sum of different, non-consecutive Fibonacci numbers. So let me show you how to do this. You always start by, well, here we're going to take 2,000. I'm going to show you how to do it. First of all, take out the largest Fibonacci that you can from 2,000, and that would be 1597. And let's circle it up here. That's the first one. So I want to write plus, and I want to get other non-consecutive Fibonacci's whose sum will be 2,000. So I'm going to take 2,000 over here, scratch work here, and subtract 1597. And subtracting, just use your calculator, you get 403. Okay, so 2,000 is 1597 plus 403. But I don't want to put 403 there because that's not a Fibonacci. So what I do is take out the largest Fibonacci I can from 403, which is 377. The biggest Fibonacci less than 403. So I'll write 377. but then I need to subtract it from 403 and see what I have left. So subtracting 377, again, just use your calculator, we have 26. Well, the biggest Fibonacci in 26 is 21. And that leaves 5, which is a Fibonacci, so I'll just write it. So notice we had 1,597, 377, 21, and 5. And you notice that those are distinct, different Fibonacci numbers, and they are non-consecutive. They're not right next to each other. If you come out with an answer with two Fibonaccis that are next to each other, that's not what we're looking for. But of course, two Fibonaccis that are next to each other, if you add those together, they're a Fibonacci too. So you check your work if that happens. You should come out with a sum of non-consecutive Fibonaccis. You could add these up on your calculator and see that it indeed works.